To another video of Math Magic with Jen. We're continuing our discussion on primes, but this time we're going to look at prime factorization, and I'm going to show two ways to do this, factor trees and factor ladders, so you can decide which one you like best. Okay, first off, what is prime factorization? The idea is to take any composite number, remember composite means not prime, and rewrite it as only a product of prime factors. So, for example, 12 is 2 times 6. Well, 2 is prime, but 6 isn't. So that is not a prime factorization. Well, what if we switch to 3 and 4? Well, 3 is prime, but 4 is not prime. It's composite. So how do we do this? Okay, so basically both of these are fails. Neither of these are technically a prime factorization. I need only prime numbers multiplying each other. So I'm going to show you two methods. The first one is a factor tree. Okay, so you're going to take your given number and find any pair of numbers that multiply to it. Okay, so over here I've got the number 12. So we would find any two numbers that multiply to 12. So we could do 2 and 6, 3 and 4. It can't be one time itself. So I lied. It can't be any pair. You can't excluding one in itself. So if you did 1 and 12, that's not good. Yeah, no, sorry. Okay. We're gonna write those two numbers and we're gonna have them branch off. That's why it's called a tree, branching off. And so if you were using 2 and 6, we'd use 2 and 6. If you were using 3 and 4, use 3 and 4. Okay. Now, if either of the two numbers is prime, circle it. So 2 is prime. If it's not, you're going to find a pair that multiplies to that number. So 6 is not prime, so we want two numbers that multiply to 6, which are 2 and 3. And those are prime, and those are prime. And once all of your ends are prime, you're done. So our prime factorization here is to multiply all three together in a list. So either 2 times 2 times 3. If you have talked about exponents, you could go that route. Okay? Just depends on if you've introduced the idea of exponents or not. But otherwise, you could just have this as our final answer. So this is a product of only prime numbers. Okay, now you're probably wondering, why did I leave this one behind? Okay, so what you can do is, I said that you can do any pair, excluding one in itself. Okay, so here, if I have 3, it's prime, but 4 isn't. Two numbers that multiply to 4, 2 and 2. So I wanted to show you this because as long as you're choosing pairs that actually do multiply the original, you'll get the same list. I got a 3 and 2 2s, but guess what? That's the same list. It's unique. Okay. All right. So you can have bigger numbers, smaller numbers, you can have them lopsided, whatever. And so I'm going to go ahead and show you the example of 48 here. So you can choose any pair of numbers that multiply to 48. So I have to admit, I would probably, like I see 48 and I think of 6 times 8 because of my multiplication tables. But you could use 2 and 24, 3 and 16, 4 and 12. There's a list, okay? Now I will say, neither 6 or 8 is prime, so I'm gonna have some breaking apart to do. So 6 is the same thing as 2 times 3 or 3 times 2. So I need a 2 and a 3, and both of those are prime. And 8 would be 2 times 4. And oh, by the way, now 4 is not prime. We gotta go break that one down. So it looks like 48's gonna be, what is that? 1, 2, 3, 4, 4 2s and a 3. Or 4 2s and a 3. Awesome. All right. Let's go ahead and try a big number. Why not? Okay. 270, when you have a big number, sometimes students don't know where to start. I mean, you could just divide it by two until you can't anymore. Other students might notice that it's got a zero, so 10 should divide it. I mean, honestly, you can start anywhere, but if you started with 27 and 10, okay. Now, some students may see that 27 and think it might be prime, but it's not. That's three times a nine. That three is prime. The nine is not prime. Nine is three times three. What? And then 10 is two times five. All right. So I've got three threes, a two, and a five. So three threes. And I could write a two and a five on the end, but I think I'm going to put the two at the front and the five at the end. So it's like in cute numerical, but it doesn't matter. You could have it in any order as long as I have three threes, a five, and a two on that list. Okay. Now, for me, this is how I learned prime factorization many years ago. We did factor trees. There's a new method in town. I mean, it's not that new. It's been around for probably at least a decade or two, and it's called a factor ladder. So if you just watched me do these factor trees and were like, thumbs down, Jen, I did not like that. Okay, let me give you another option. I'm fine. Okay. So a factor ladder is a more it has more steps, a checklist. It's not so all over the place, right? Factor tree is a bit all over the place. You get a lot of choice. So for students who like choice and like to kind of bounce all over, they may like that. For those that want the rigor, the straight and narrow, you tell me what to do and I'm going to do it, factor ladder. Okay. So you take your given number. Great. That's a great first step. Take your given number. Great. What am I supposed to do with it? Okay. What you're supposed to do with that given number is you're going to actually do like an upside down L or an upside down division. Should write that, but there you go. Okay. Now, what you're going to do every single time, no matter what this number is you're going to try to divide it by two if you can. So can we divide 12 by two? Yep. And then it says keep doing it. So if you can divide it again, do it. So I can divide it again. Okay, now I'm going to stop right there. This is the whole ladder part. It kind of looks like a ladder. Oh, okay. All right, now you switch. Once we can't do two anymore, we're going to switch to the next prime number. So let's talk about our list of prime numbers. Keeps going, but there's at least the first six prime numbers. So once you've done two, you're now going to switch your attention to three. So can I divide three by three? Yes, I can. And what happens is you're going to keep doing this until you have a one down here. So we're done. This is it. Okay, now, where's my answer? My answer is all the numbers up front. So this is 2 times 2 times 3, which is the same list I got a little while ago. Okay. So, we're gonna try it again. I'm gonna do it actually with the 48 and the 270. Okay, and we're gonna follow this. So we're gonna divide by two until we can't anymore. Then we'll divide by three until we can't anymore. Then we'll divide by 5, 7, 11. You keep going until I just have one on the end. Okay, so let's try it with 48. So I'm gonna start by dividing it by two. And if I can divide by two again, do it. And if I can again, do it. Can't anymore. So this kind of a nice little run here. I got to divide by two 4 times. All right, awesome. Now, once you divide by two, our next number that we're going to divide by is 3. And for this problem, we're now done. The second you get a 1 at the bottom, you're done. So our prime factorization is 4 twos, oops, and a 3. Boom. Okay. All right, now, one more time. Obviously, this goes faster if you're good with arithmetic. If you're bad at arithmetic, it's going to take a while. That's fine. You're still a good, awesome human being if arithmetic's not your jam, but I'm just letting you know. If you have to take a minute, take it. Your students, if they have to take a minute, let them. Don't shame them about being fast or slow. Just let them come to it when they come to it. Okay, now we're going to divide by 2. Now, they may actually need some scratch paper over here to divide this by 2. Unless you want them to use a calculator during this exercise. That's your choice. I'm not, no shame, no shame. That may sound like I was shaming you, like your choice to use a calculator. No, 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 you can't. It's up to you. I'm just telling you that you would either have to do long division, do it in your head, or use a calculator, but I'm going to get 135. Now, 135 is not divisible by 2. So now we're going to try 3. And let's see if 135 is divisible by 3. Goes in 4 times 412. And yeah, 5 times for 15. Holy cow. Right. Whew. All right. Uh, by the way, we're supposed to keep dividing by 3 if we can. Okay, so we haven't had this happen yet of dividing by 3 again. And dividing by 3 again. And then I can't divide by 3. So then my next prime number would be the number 5. So there's my list. A 2, 3 threes, and a 5. Okay. Woohoo! Now, interesting fact. Yeah, we got the same answer. Whether you use the factor tree or the factor ladder, you got the same answer. And that's because of something called the unique factorization theorem. So what happens is that you're either a prime or composite. And if you're a composite, not prime, then you can rewrite it uniquely as a product of primes. So what that's saying is that all composite numbers have a unique factorization. So like 48 was 4 2's and a 3. There's no other number that has exactly 4 2's and only a 3. If you have 4 2's and a 3, you're only getting 48. Okay? The number 12 has 2 2's and a 3. So every single composite number has a prime factorization that is unique to them. And it doesn't matter if we use a factor tree or factor ladder, you're still going to get the same thing. This is also called the fundamental theorem of arithmetic. So it has 2 names. Don't know why it has 2 names, but it has 2 names. So you can refer to it either way. But yeah, the most important part is understanding that it doesn't matter which method you use, you're gonna get the same prime factorization. All right, that was another one in the books. The next set of videos is going to be kind of interesting on divisibility tests. So keep your eye out for a 2-part video on divisibility tests. But until then, keep working on primes, prime factorization, and I hope life is treating you well. Have a wonderful time working on that. Bye-bye.